In this video, we're going to be finding Maclaurin and or Taylor polynomials or series. So here's the video where we actually find out how those series were arrived at for, especially the four parent series that we're expected to memorize. They just didn't appear out of the blue. They were created by using some set of steps. Okay, so this is the video that's going to show us how we're going to create those series. Some things to take note of. I'm going to be talking about polynomials and series in this video. Just to remind you, a polynomial is going to be a finite number of terms. It's going to end. It's not like a series that continues on and on. So if you're asked to find a Taylor polynomial or a Maclaurin polynomial, you're going to have a countable number of terms, that you're going to be finding. All right, so here we have a function has n derivatives. So if we have a function and it's differentiable and it has a certain number of derivatives at its center, then we have a polynomial. That's what P stands for here. Then we have a polynomial right here that can approximate that function. So it's just like saying with those parent series that we have, choose the first 5 terms, and those first 5 terms would pretty much seriously, mimic what that function's doing near the center. All right. So this is called the nth degree Taylor polynomial for the function, whatever it is, at C. And it's named after Brooke Taylor, this English mathematician. All right, and then if C is 0, then of course the polynomial you can see is going to reduce down to a Maclaurin polynomial. And that's named after yet a different English mathematician. Okay, so this kind of gives us an idea of how we're going to form those Taylor polynomials or those Maclaurin polynomials. Okay, well, let's look at the Taylor series right here. Okay, well, a Taylor series just indicates that we have an infinite number of terms, so we're going to have an expression for the nth term, such as this. And then, of course, we can collapse this into some concise notation using the sigma notation. If the center is 0, it's called a Maclaurin series. All right, if C equals 0, the series is called, it looks like that's a little typo there, a Maclaurin series. Yeah, so before looking at some specific examples, let's look at the structure of this polynomial. All right, this is a functional value at C. So it has to agree with the functional value on, the function. This is plus. Let's look at the next term, f prime of C, the derivative of the function we're trying to approximate, evaluated at the center. Okay, but right here it kind of gets interesting right here. This is the structure that we're going to be referring back to. Look at this coefficient. I'm going to call that a sub 2. I can take all of that and say, you know what, that coefficient can be represented with a sub 2. And that's how we saw it in the power series notation, with a and a subscript of n for the nth term. Okay. Look at this quotient right here. This whole quotient right here can be simplified and be expressed with the coefficient a sub 3, etc. So this is the coefficient a sub n. All right, I'm going to work backwards in here. So let's look at this actually right here. I could create a fraction and put f prime of c, the first derivative, over 1 factorial. So this is a sub 1. Okay. All right, and so kind of looking at maybe one of these outside of the context of this polynomial, let's consider a sub 4. What would that look like? Okay, if I were to generate the next term, of this Taylor polynomial, what would I expect a sub 4 would look like? Well, it appears that all these coefficients are fractions created by the appropriate derivative divided by the appropriate factorial. So for a sub 4, this should be 4 factorial, and this would be the 4th derivative. I'll put a 4 up here, evaluated at the center. Okay, so what is the coefficient for the 5th degree term? I think we'll see where this is going. Okay, well that would be a quotient created by the fifth derivative evaluated at the center divided by 5 factorial. Okay, so an expression for the nth coefficient, okay, right here it continues, okay, is given right there. It's the function, whatever we're working with, the nth derivative at the center divided by n factorial. So that's kind of important to point out and note. Okay. All right, so let's take a look at some examples then of how to create series that represent functions. All right, so for example 1, we're asked to find the Maclaurin Polynomial. It's going to end fifth degree, so the highest exponent I want to go to is 5 for this function. So it's actually just going to be the first 5 terms of the parent series we've been working with. But so when we study back previous, what I just scrolled away from, okay, what we need is the functional value at the center, okay, and then some derivatives. I guess what, 5 derivatives to get to the fifth degree. So just kind of organized work over here. It's Maclaurin, so I'm going to evaluate the function and all of its derivatives at c equals 0. So sine of 0 is 0. Oh. All right, let's find f prime of x, cosine x. So f prime is 0. So the cosine at 0 is 1. And we're going to continue. F double prime, negative sine, evaluated at the center is 0. Okay. F triple prime, evaluated at x is negative cosine, evaluated at 0, negative 1. Fourth derivative, I'll put a 4. Looks like I'm going to be back to what I started with, sine x. So there's a pattern here. The fourth derivative at 0 is 0. Fifth derivative, cosine. Fifth derivative at 0. Cosine of 0 is 1. Okay, so it looks like we have all the information to build at least the coefficients, okay? And by the structure of what we saw previous in the definition of the nth degree Taylor polynomial, we should be able to build the fifth degree polynomial. Okay, so I'm going to kind of come right here. And I'm going to say the polynomial of fifth degree in terms of x for sine x. So this fifth degree polynomial, if you graph it in the same window as sine x, it should model sine x within a certain distance around the center 0. Okay, so looking back up there at the structure, what we need is the functional value at 0 plus f prime at 0 divided by 1 factorial times x minus 0 to the first power. Yeah, so that's going to be unnecessary, but I just wanted to show you the complete structure. Next term, the coefficient is going to be the second derivative that we got over here, evaluated at 0, divided by 2 factorial, and that's going to be actually x minus the center squared. So that'll just be x squared when we clean it up. Fifth degree, so I've got to go up to the fifth power. So this next coefficient is third degree at 0, 3 factorial, okay, x minus 0 cubed. Because I'm going to run out of room, I'm going to go ahead and just put x I'm just going to put x there, x to the fourth. Okay, so notice the degree has to match the the denominator here and match the appropriate derivative for us to use this formula, this Taylor formula. And finally arriving at the 5th degree term. And this is going to be x to the 5th. Okay? So a little cleanup. The functional value at 0 was found up here at 0. Right, the f prime at 0 was 1, so this numerator will become 1 over 1 factorial times quantity x minus 0 is just x. So that whole term collapsed to x. Okay, the second derivative at 0, coming back over here, it's 0. So 0 over 2 factorial 0, 0 times x squared is 0, so we don't have an x squared term. So move on to the 3rd degree. The third derivative evaluated at 0 is negative 1 over 3 factorial. So I'm going to have minus, I have 3 factorial in the denominator, and I'm just going to have an x cubed on top. All right, the 4th degree term, well, the 4th degree evaluated 0, 0, so we don't have those those even power terms. Okay, so we're only going to have the odd power terms. So think back to the parent series we've been working with, and this agrees with what we found. All right, so the 5th degree at 0 was 1, so we get to stack that as x to the 5th over 5 factorial. Okay, I'm not going to do the dot, dot, dot because we have just succeeded in getting a 5th degree Maclaurin Polynomial for sine x. So graph this in y1, this in y2, and these two graphs are going to agree for some radius. That's it. That's how we create them. Okay, if you were asked based on this pattern, what is the 6th derivative evaluated at the center? Well, the 6th derivative would have to be 0 because we're not going to have that even term. You could be asked various questions about something that's given to you. For example, you could be asked, what's the coefficient of the 7th degree term? Okay, if you were asked, well, what's the coefficient, then just think about that. If you were asked, what's the coefficient for the 7th degree term? Okay, well, a sub 7 represents the coefficient of the 7th degree term, so you would have to have division by 7 factorial, okay, and the 7th derivative evaluated at 0 here. Well, if you did have that term, the coefficient would be 1 over 7 factorial, so that must mean that the 7th derivative evaluated at 0 must be 1. So if we knew a sub 7, which we would from the pattern, is 1 over 7 factorial, we could set it equal to what we know created it. And it's very easy to see then that the 7th derivative evaluated at 0 would equal 1. So just some interesting kind of questions they can ask you based on kind of a built series. So example 1a, find a Maclaurin series, a series. So the only difference is we're saying series now. Well, you'd go about producing the series the same way we did here. Okay. You just wouldn't call it a polynomial. So just stealing what I had up here, if I'm going to create a series, okay, it would be up to me if I'm creating that series to come up with an expression for the nth term. And that probably is a challenging, thing for us to do. Okay, well, how do we come up with a representation for the nth term if we've used Taylor's theorem, so to speak, to kind of help us create this series? All right, if it's up to us to determine an expression for the nth term, kind of a rule of thumb that might help you in determining, how to represent it with n. I don't know. I try and start with 0. As far as what I mean is I try and number the terms of my series starting with 0. So I might call this term the 0 term, the first term, the second term, third term. I'm trying to establish a relationship between the position in the series and maybe the exponents. I'm trying to look for some kind of pattern or something using n that would help me develop this. Okay. So start with 0, see if that helps you determine this term right here. One of the first things you probably notice is it's an alternating series. And if the first term is positive and we start counting with 0, then n is going to be 0. So that would make sense that would produce a positive. If n is 1, then it'd be negative, and that's all going to work there. Okay, and then you just want to establish a relationship between the position in the series and the exponents, etc. So we know it's a power of x, so x raised to the, and sometimes it's easier to look at later terms, like what do you do to 3 to get 7? And it has to be the same set of steps that you do from 2 to get 5 and 1 to get 3. How do I produce these numbers? Well, you're doubling the position number and adding 1. So, and we've had experience with this, we knew that, but it's also good to look at. So you're doubling the position number and adding 1, and then that's also what you're dividing by in factorial format. So we just created the Maclaurin series by using the set of steps that are indicated by the formula at the beginning of the page, the top of the page. All right, so just more practice. And I think, looking at the time, that's going to have to be done in a different video.